Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.
I'd like to thank Tristan Martin, Roland Paul, and the entire Enclustra events team for inviting me here today. And I'm really happy to share with you the good news about our Versal AI Edge and RFSoC devices. So to kind of set the stage for our discussion, I'd like to talk a little bit about the problem that we're trying to solve here. So the conundrum that is being faced is requiring this new compute paradigm is there's a need for AI compute. This is something that's cheap to the data center. The trouble is to get low latency, you can't wait to send a message from your application that's running at the edge, say that's a vehicle driving down the street. It may be a computing device inside of a factory on the assembly line. You can't wait for that device to send something up to the data center and then get a message back down. So perhaps thousands of milliseconds later, that low latency can definitely kill your application. So the need to have low latency on the device, also having low power, not everybody can afford to fit a data center in terms of a power budget inside of a vehicle. That's usually a non-starter for vehicle applications. And then also having the safety and security, having the ability to securely sign and encrypt all of your pieces of firmware inside the system to give you that level of security that was talked about earlier in the presentation this morning. So this unique challenge, and what we're presenting here is that a single architecture can't do it alone. You're not going to be able to achieve that with a CPU alone. You're not going to be able to achieve that with scalar processors alone. You're not going to be able to achieve that even with programmable logic alone. So what we've done is we've introduced a platform that has all these capabilities built into it, and we'll show a little bit about how they all work together. But the low latency, I like Christian's presentation where you're talking about low latency. I did like a little bit of research. It turns out latency is the #1 reason to shift computing down to the edge system itself and away from the data center. So what we talked about, that round trip being kind of the killer in a lot of AI edge applications that depend upon services that are being run in the cloud. That's what's fueling this push towards getting everything onto the edge device itself and away from the data center. So if we talk about what the Versal AI Edge architecture looks like from a high level capability, the key feature that we're introducing here are these adaptable engines, the scalar engines, and the intelligent engines that you see here on the right-hand side. The adaptable engines, these are our traditional programmable logic that you can tune for adapting to any workload inside of the device. The scalar engines, these are the embedded computing pieces that you've seen before, the ARM computing complexes that are available inside of the device. And then we've also introduced with the Versal series these intelligent engines. And so I'll talk a little bit about how these intelligent engines on this device have been optimized for AI compute workloads. But there's also intelligent engines on our Versal AI core devices that also can process diverse DSP workloads for our higher mass computational demands. We have accelerator RAM that's available on these devices to serve as local memory, so you're not having to spend as much time to do DDR accesses for these tightly nested functions that you find inside of convolutional neural networks that are being processed at the edge. And this is going to help enhance our AI compute by reducing that demand upon the DDR memory. The other thing too, I'll talk a little bit more about this in detail in a later slide, but we have a programmable network on chip, or NOC. And so this is going to give you the guaranteed bandwidth that you need between the different pieces of the system where you're trying to offload your workloads from the software world. We have a video decoder unit that's capable of doing H2.64, H265 decoding up to 4 by 4K ultra high definition. This is, if you can think of this as kind of like a video aggregator system, you can connect multiple video streams that are maybe sending RTSP streams that are encoded in one of these protocols. You can decode that and do your edge AI processing on this device from multiple incoming streams. On the left-hand side, we have the features that you would expect to find inside of an embedded computing device. We have PCI Gen 4, so you can still connect this up to an x86 platform as an accelerator for x86 platform. This would be a companion compute acceleration platform for that. We have the DDR4 memory capability on this device for local memory on your board. And we continue our transceiver leadership with this broad range of 1 gig to 25 to 32 gig on this platform that's power optimized for edge applications. We have programmable I/O, giving us the ability to interface to any sensor or any sort of peripherals on our device. And this includes up to 3.2 gigabits per second MIPI interfaces. So if you have, as was discussed in the earlier session, you have multiple MIPI sources that you're trying to pull into a single device, you're going to need lots of I/O in order to do those many cameras that you wouldn't be able to get that many camera MIPI channels on other devices. So this makes this an incredibly useful platform for the multiple camera solution. And then, of course, we have our multi-rate gigabit Ethernet, 10 gig, 25 gig, and 40 gig capabilities on the device itself. So if we dive into what the AI engine tile looks like, you can see this is an ISA-based vector processor, and this is the part that's shown here in the middle in green. This is a VLIW vector processor, which has AI and 5G specific vector extensions. And it's running at 1 gigahertz in its lowest speed grade, and that increases for faster speed grade devices. It's software programmable. You can write C and C++ code, and there's a compiler, which we include inside of our tools, which will schedule and compile all the instructions to run on these devices. And then next to the AI engine core is the local memory, this local data memory you see here. There are multiple banks, and that can be accessed using the interconnects by the neighboring tiles and cores, as shown by the red bidirectional arrows on this graphic. So the shared interconnect shown here in navy, this is one of the key differentiators of this architecture. This is non-blocking deterministic interconnect at 32 bits, which allows you to communicate with the other AI engine tiles inside of the array. And then finally, within the local memory, there is also data movers, which help move the data for this local memory to non-neighboring tiles or back to the PL. And that can be done in parallel while the AI engine is computing the kernel results. And another interface that's really important to mention here too is this cascading interface. This is the one shown in green. This enables you to transfer partial results from one AI engine tile to another one in order to complete the compute if more compute resources than what can fit in a single AI engine is required for your end application. So for FPGA designers, you can kind of think about this as a cascade in DSPs to build multiple larger multipliers and things like that inside of a system. So let's see what this means with respect to the capability the AI engine brings to the table versus the previous generation. So Roland had presented like a roadmap of how you'll be able to migrate from the MPSoC based SOMs to an AI engine, Versal AI edge type compute SOM in the same form factor. And so let's take a look at like what that would look like in terms of compute integration. So we talked to lots of customers. This one comes from a customer application who's identity will be protected here, but we're overly simplifying the application to kind of show the level of integration you're able to achieve with Versal AI Edge. So in this application, we have 3 different devices. So we have 2 MPSoC devices over there on the left. One of the MPSoC devices is connected to a image sensor. So you can think of this as a forward-facing camera. This is a higher resolution sensor and needs to gather lots of details about where the car is headed. That's also connected up to another Zinc UltraScale Plus device. This has 4 image sensors, so think of this as the surround view. So you have a camera for each of the 4 directions of the vehicle to get a 360 view of the vehicle. And then finally, inside the vehicle is a driver monitoring system, and this is implemented on our Zinc 7000 architecture. This, this may have special requirements, like maybe it's a RGB-IR sensor to where you're illuminating the cabin with infrared, and so you need to be able to have that vision capability at night when the cabin's not illuminated with regular visible light. You can illuminate it with IR light that's invisible to the naked eye. So we had this previous application that was being used on a vehicle, and so they wanted to know what level of integration they could get with a Versal AI Edge device. So with the Versal AI Edge device, we're able to achieve the same level of capability in terms of image sensors needed for the surround view, image sensors required for the front forward camera, and then image sensor required for the driver monitoring system. We also have Ethernet capability built in here as well, so we can also do the processing that's required for LiDAR, and we can also do the local processing. So for feedback to the driver about what is going on inside the system, we can also drive the display from the same device. So in terms of integration, we actually are able to achieve more compute capability. So we go from same sort of order of cameras at 4 tera operations per second on the AI inference application, up to 17.4 tera operations per second on the Versal AI Edge device. So that's about a 4.4x increase. In terms of area that's being consumed by this, because you have to have 3 devices in the first application, we're able to reduce this down from a 1,259 square millimeter application down to a little over 500 square millimeters for the Versal AI Edge. So about a 58% reduction in area of PCB space that's needed. And then in terms of power, you could say it's roughly about the same, maybe just slightly less with the Versal AI Edge device in terms of overall power consumption. So you can see this is a really great way to take a lot of complexity that you may have been doing with multiple devices and integrate this down into a single AI Edge device. So if we talk about what is this key enabler of the AI performance per watt that we're able to achieve with this, these new AI engines are very exciting. They're a breakthrough architecture that was announced with our first Versal device. This was the Versal AI core device. So this is an immense 2D array of vector processors, and each of them carry a massive amount of compute for various data types, not just AI inference, but for other workloads like beamforming and radar processing. On this specific iteration of it, this is the AI ML that's using. We've optimized that computing for machine learning. By doubling the multipliers that are used in the system, we've doubled the N8 compute resources that are available, and we've also added native support for int4 and bfloat16 operations as well. We've doubled the data memory from 32 kilobytes to 64 kilobytes, and we've improved the localization of that data by putting it very close to the AI engine tiles. So the new memory tile, this can do up to 38 megabytes across the entire AI engine array, and this gives you higher bandwidth memory access than what you're able to find on a DDR memory interface. So it gives us very good scalable and modular architecture that we're able to leverage for this. So just looking through my notes here. So this is definitely something that's proven on our Versal AI core, and we're continuing that advancement on the Versal AI Edge devices. So you get lots of questions about, well, how do I go about programming these devices? So It's a software programmable architecture. As we've seen on the AI engine, this is definitely also software programmable. So Xilinx has been successful with hardware engineers and will continue to be so and support those users with their inflow inside of the adaptable engines. And that's our programmable logic. But in terms of being able to program the whole entire system, we definitely support C and C++, as well as the popular AI frameworks of MXNet, PyTorch, TensorFlow. And then on top of that, we also have these Vitis libraries that are available for our tool. So these are just a small subset of them: the 4G, 5G radar library, the AI library, and probably our largest and most popular library is the Vision library. So this Vitis Vision library, you can think of these as they're written in C and C++, but they're optimized for use with our HLS tool, and they're OpenCV. Each of them have an OpenCV signature that allow you to create hardware accelerated OpenCV functions. And you can even optimize it even further by having a streaming interface between each of the OpenCV blocks. So you're not buffering your image data inside of an intermediate buffer. You're able to stream the outputs from one block into the next block to create a vision pipeline using these Vitis Vision libraries. So once you've designed your system, you compile it using the AI engine compiler and our Vitis tools. This allows you to run your platform through different abstraction levels. You can write it from an architecture overlay point of view. You can write it from a data flow point of view using the Vitis libraries that we have available. And one other thing that I'll mention about the Vitis libraries, these are libraries that we've made available on our GitHub. They're open sourced under an Apache license, so it's very permissive open source license. You can take them and modify them however you see fit. There's no licensing or royalties that you pay back to AMD for those. So those are something that we include. And then from a kernel programming perspective, you can create a data flow using your own user-defined libraries and implement that within your system as well. So different levels of granularity at which you can program at inside of your system, depending on how your developers are working and what sort of frameworks you're operating within. So I mentioned this before. So this is our network on chip. This is bringing all the engines within the device together. So network on chip, that's our NOC. This gives us a massive bandwidth and programmable network on chip that abstracts away the hardware and stitches these heterogeneous engines that you see inside the device together. So unlike a typical NOC in an ASSP or an ASIC, this can be programmed for different data flows between the high-speed IOs and the engines, and the ability to prioritize between throughput, latency, and even the bit widths between the different blocks. So traditional routing in the FPGA, like adaptable engines, is available to meet specific latency and determinism requirements. But it's not only about getting from point A to point B. The NOC also gives you the ability to intuitively compartmentalize the kernels that you create on the adaptable engines with easy entry and exit points. So you can get data from I/O to different portions of the fabric without having to worry about any sort of complex floor planning inside the device. And it's hardened connectivity to Versal's integrated memory controllers and PCIe without any place and route involved. So you may be wondering, how do you go about evaluating this new technology? And so we have really good news about this as well. This is our VEK280 Versal AI Edge evaluation kit. It's the board that's being shown in the demo at the back here. These are our evaluation platforms that AMD creates. There's also evaluation platforms like the one that's being offered in the raffle here from our partners like Enclustra. These are platforms that are used to evaluate the technology. These aren't end products. They're designed to sit and operate on your desk for you to use in developing and evaluating and exploring the use of the tools for creating an end solution. But this board is equipped with a Versal AMD AI Edge VE2802 piece of silicon. That's where the VK280 number comes from. It has the same AIE ML array that I talked about before to give you that 4 times performance per watt compared to GPU technology. And it has pre-built reference designs that are available for rapid prototyping. So what that means is what we make available on our GitHub are these targeted reference designs. These are not only pre-compiled binders that you can run in order to get something up and running quickly on your platform. But we also provide all the source code that we used in order to build those binaries so that you can leverage that as a starting point for your own platform and then kind of spiral outwards from that core capability towards the end application specific use case that you're looking for. So great starting point that can help you accelerate your own development. It has PCIe Gen 4 capability. It has a SFP28 for doing networking, additional networking capability. It has HDMI 2.0 and then KNFD for automotive applications as well. We have this 12 gigabytes of LPDDR4 memory on there. And we also have an FMC Plus interface for I/O expansion. So this is this large rectangle connector that you see up at the top. This is a FPGA mezzanine connector. And so we work with lots of different partners to come up with different sort of FMC plugin modules that you can use to customize the character of the board towards a specific end application. There's video boards that you can plug in. There are camera boards that you can plug in. There's high-speed analog to digital converter boards that you can plug in to help you customize it for a specific end application. Excuse me. Finally, I will mention this is something that is open for order entry this month. So you can go on to the Xilinx.com website. And we will be shipping the first batch of these boards in November. So there's the URL for it, and you can access that on our website. Okay, so moving on to scalability. The Versal AI Edge portfolio is made up of these 7 devices. So you'll see a tremendous amount of scale that's available from edge sensor to CPU accelerator. We'll highlight a few things on this table. So the smallest device that has just 8 AI engines and it runs at sub 10 watts, while our largest device, which is the one that's on the BEK280 board, this one has over 300 AI engines for over 400 tera operations per second. Also note the throughput advantage due to the native Int4 capabilities on all these devices. So you might ask why to scale such large devices, and the answer is that many of the automated applications that developers face nowadays need these powerful accelerators in certain parts of the system. So by having these different nodes that are powered by a single architecture, it gives you that system-wide scalability. Okay, so that brings me to the end of our Versal AI Edge presentation. Let me switch over to our RFSoC. I wanted to dive in a little bit about RFSoC because Roland talked earlier about how there's an RFSoC song that Enclustra is working on as well. So very excited to hear about that. So here's what we're doing in more detail inside of an RFSoC device. So it's basically the same thing that you find on a Zynq UltraScale Plus MPSoC device in terms of processing capability. But we've added in these RF analog to digital converters and RF digital to analog converters in error correction cores that are placed on the same die as the processor subsystem and the programmable logic. And this is all monolithically integrated. It's not a 3D IC architecture. And everything you see here, other than the blue blocks at the bottom, is already shipping in other devices in full production. So you can have a high confidence in the rollout of this RFSoC family. And as in the MPSoC family, this device includes a quad-core 853 64-bit application processor and dual ARM R5 real-time processor. And we have integrated within the device the FPGA fabric that's capable of 33 gig transceivers and 100 gig cores that can integrate with PCIe or Ethernet. The fabric's based on the same 16 nanometer FinFET, and the same thing for these new analog signal chain error correction blocks that you see up here. The ADCs run in 8x8 mode at 4 gigasamples per second, and the DACs run at 6.5 gigasamples per second. And this features a complete hardened signal processing subsystem, and that runs in 16x16 mode, and the analog to digital converters for that run at 2 gigasamples per second. The error correction block that you see up here, the FEC block, is based upon soft decision decoding method, and this supports LDPC. This is low density parity check coding schemes to meet both 5G and DOCSIS 3.1 standards. as well as turbo decode that gives you the compatibility you need for existing 4G LTE standards. So these are the key values or benefits for integrating RF sampling converters inside of a system. You get the direct RF sampling. We've integrated this very specific type of data converter, which is capable of directly sampling the RF frequency carrier or generating a RF carrier directly. What this means is that all the signal processing is done after the ADC and before the DAC can be carried out in the digital domain prior to conversion into the analog domain. And this approach enables this highly flexible and programmable solution. And it's well beyond anything that can be implemented using analog signal processes with discrete parts. And we'll look at this in a little bit more detail in some of the later slides. The other advantage is that you get reduced system power. So the data converters themselves are built using our advanced 16 nanometer technology. Another big advantage to integration is the elimination of the external I/O or SerDes power that is required to interface external discrete data converters. This was something that was talked about earlier in Harry's presentation for traditional RF software-defined radio systems. And we'll also look at some of the power implications with an example later on. The other thing too is the footprint reduction that you get with this system. One of the key technologies that delivers high throughput and quality of service in the next generation of wireless systems is this use of spatial modulation techniques like MIMO and beamforming. These are applications that this sort of device is really good at. And the integration of high channel counts and the associated JESD interfaces makes that direct RF sampling solution viable in these types of applications. And then finally, shorter design cycle. So one obvious benefit of direct RF sampling is the elimination of lots of discrete and even integrated RF components found in the typical RF lineup. And these components also lack the significant programming capability that require lots of optimization from various RF use cases. And this means that new hardware and PCB designs and verification can be implemented with direct RF subsampling. Much of that configuration can be carried out inside of the digital domain and facilitated by the use of software tools that allow a lot of flexibility with a common hardware platform. Let's move on to the next one here. So all of our FPGAs address multiple markets, and the Enclustra Scale Plus RFSoC is no different. The three main markets that you see this being used in are wireless, wired, and aerospace and defense. And wireless is pretty obvious, but we should mention that we play not only in the sub-6 gigahertz radios, but also in the 5G baseband. This is due to the SD FEC block, and then we can also do millimeter wave. And I'll talk a little bit about that more later. The aerospace and defense is also pretty obvious with key application in phased array radars, and especially multifunction phased array radar, or MPAR, where thousands of these radiating antennas are used to steer radar beams, to detect and analyze aircrafts and incoming weather systems. A not so obvious market is cable access for what we call remote PHY node in DOCSIS 3.1. And the other strong markets are in satellite for both the ground stations and the low Earth orbit satellites. There's other applications inside of test and measurement, and even on LiDAR, this is something that can be used. So this is our RFSoC roadmap going from 16 nanometers to 7 nanometers. So our Gen 1 has been in production for quite a while. We recently announced our Zinc RFSoC digital front-end device that you see here second to the right. This is something that has the highest bandwidth on the device, and it also has the adaptable digital front end that's available on it. So as we look into 7 nanometers, the planning is to move to what's called the AIRF device. And so this will have even higher bandwidth capability on it as well. So we're really looking forward to partners like Enclustra deploying their own RFSoC SOMs and making this something that is very easily integratable into an end system. So let's talk a little bit more about that latest device, the RFSoC digital front-end device. This is also based on our Xilinx 16 nanometer ultra scale technology. It includes that quad A53 processing system, gives you the adaptable logic that you need inside of the system, and also gives you our 32 gig GTY transceivers. And it's also software compatible with MPSoC family that you find on a lot of the Enclustra SOMs. The Zynq RFSoC digital front end includes a complete hardened radio subsystem that supports 8 transmit and 8 receive chains for both the FDD and TD applications. And we have these proven RF sampling converters that are based upon the Zynq UltraScale Plus RFSoC Gen 1. Hardened digital up converter and digital down converter blocks. These will convert the baseband for the RF sampling converters and vice versa. Those can be configured for all the wireless frequency plans. And we also have this crest factor reduction, or CFR IP block, that's based upon Xilinx's soft IP, but it has improved performance and supports up to 400 megahertz of instantaneous bandwidth, or IBW. We also have digital pre-distortion that's based upon Xilinx IP, and this supports same 400 megahertz of IBW with the latest wideband gallium nitride power amplifiers, and that's used in a lot of 5G deployments. We have a mix of additional signal processing blocks that are such as resampling, and we have equalizers included also. The entire digital front end path from the baseband to the RF can be implemented as hard IP inside of this system. So this is the industry's only 400 megahertz IBW direct RF sampling digital front end solution, operating up to 7.125 gigahertz. And when we use it as a FR2 IF transceiver, the RFSoC can actually support up to 800 megahertz of IBW and 16 megahertz of IBW in 2T to R applications. So this is a great achievement in processing power. And you may be wondering, well, why is that important? It's important because it comes down to the performance and the flexibility for base stations and various carrier needs. So when you consider all the frequency bands that are involved and the carrier configurations that operators support globally, the number of radio variants would be pretty unmanageable if you had each radio being unique in terms of implementation. So this wider bandwidth enables the single radio SKU to support many more frequency requirements and process higher data rates that are required for 5G deployments. We also have multiple band capabilities that enables a lower cost, as one radio can support these multiple standards. And we also have 400 megahertz IBW in the C-band. And in North America, the C-band is 280 megahertz. And the tri-band allocations are FTDD below 2.5 gigahertz. So lots of capability inside of this platform for consolidating down your different SKUs onto a single hardware platform that's capable of supporting multiple areas of the spectrum. So our Zynq RFSoC digital front end that can support the heterogeneous 5G networks all the way from small cells up to massive macro cell solutions. And right here, I wanted to give you a look at a block diagram for the RFSoC to kind of understand how all these hard blocks work together. So the hard IP blocks, those are arranged physically on the device, and that's consistent with the data flow that these are interspersed within the PL fabric. And each hard IP cell can be bypassed, and the PL can be added at any point inside of that signal processing chain to insert your own IP, or you can insert other pieces later on to adapt to new requirements. And so since it's an all programmable device, you can deploy those updates out to the system through over-the-air updates to update your hardware platform. And some of the IP that's not suitable for hard implementation, or that may depend mostly upon application specific implementations, those are left into the programmable logic fabric. So in some examples of what that might be is if you're doing any sort of proprietary DPD data paths or automatic gain control or synchronization, all that can be done inside of the programmable logic, so it has that flexibility to change later on if you need it to. Also, interfaces such as CIPRI, eCIPRI, or ORAN, those can all be implemented in the programmable logic as well, and they can take full use of the 32 gigabit per second SerDes that we have available on the device. Lastly, the processing system of this device, that can be used for the configuration, DPD updates, and diagnostics on the platform. You have the capability to write all that in terms of user interface software and remote update capability that you're handling from the ARM cores and the processing system. I think I covered everything on there. I want to talk a little bit about the boards and kits that are available for RFSoC. So in addition to the board that Enclustra is introducing that has RFSoC, we have a number of RFSoC evaluation kits and boards. So starting all the way with our first ZC111 board that had the ZU28DR device on it, working all the way up to our latest board, the ZCU670 board, is our latest evaluation kit that we've deployed. And so behind these, we also have targeted reference designs that are available for you to use as a starting point for your own end application deployment. And you kind of inspire off from the source code that we provide for these reference designs to get you kind of quickly up and running on these platforms and get you familiar and comfortable with the tools. If I dive into that ZCU670 evaluation board a little bit further, this does have the ZU67DR silicon on it, so it allows you to evaluate that latest device that we have. The hardened digital front-end cores, these are again optimized for wireless applications. We have our low jitter RF sampling PLLs with clock forwarding on this board. We also have the Zynq RFSoC processor, the adaptable logic inside the same device, and this is all on a thermally optimized lidless package. Some things that you may be interested in is this is going to allow you to evaluate CFR and DPD IP with different power amplifiers on the board. It enables you to evaluate hard IP blocks for DL and UL. We have the library of these fixed designs that are available that cover a range of configurations, and for anything that's provided as a targeted reference design, you have access to the source code for that as well. So board is available for order entry right now, so you can place your order for that at the Xilinx URL shown here. I did want to talk a little bit about some of the RF tool flow and methodology. So there's RF data converter evaluation tool that's available. We have also Vivado ML editions that are available to use to design your system. And then there's also an RF analyzer debug tool that can be used with any of the RF boards that we offer. And that gives you direct API function access, so you can write something from higher level, something like Python, and it's also debug focused. And then I want to talk a little bit about some of the design methodology that's enabled on these platforms. We have interoperability with MATLAB and Simulink, so if that's where you're used to doing your algorithm design, you can do that as well and target this platform from those tools. We have the RF connectivity and integration capability. And then we have SoC design and IP integration on ours through the use of the Xilinx Vitis tools and Vivado tools. And there's a number of evaluation kits and front-end cards that are available from partners like Avnet and from Enclustra, who's also working on an RFSoC SOM capability. So you have lots of options in terms of high-speed DSP applications and avenues for which you can explore this in your next end application. All right, so that brings me to the end of my presentation. Yeah, thank you very much, Casey.
Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors. enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.